Okay, so in this problem, K is the Cantor set in the closed interval 0, 1, and f is a function which is defined on closed interval 0 to r, such that f is 1 on the Cantor set and it is 0 in the complement of the Cantor set. So now we have to check what all options are correct over here. Now, as all of us know, that Cantor set is a set which I'm going to denote by K. The Cantor set has measure 0. This is one of the important properties of Cantor set, right? So if I try to visualize this function roughly, I'm going to see that on 0, 1, this function is going to be what? This function is 1 on the Cantor set, and we know that Cantor set is a very thin set. So on that Cantor set, the function is going to be 1 and it is going to be 0 otherwise, right? In the complement of Cantor set, this function is going to be 0. So for very few x, the value of the function is going to be 1, otherwise the function is going to be 0. Correct. So this means that the function f that I'm talking, the function f is 0 almost everywhere. That is the definition of the function being 0 almost everywhere. For a set on which the function is not equal to 0, that set has measure 0, right? So who is that set? That set is the Cantor set K, where the function is not equal to 0. Now, if I look at this function carefully, we see that the closed interval 0, 1 is divided into two sets, which one is K and other is K complement. These two sets are disjoint. On the set K, the function is defined to be 1. On the K complement set, the function is defined to be what? The function is defined to be 0. In which interval? In the interval 0, 1. This means that this function f is actually nothing but characteristic function of the Cantor set. Right now I know that K is a measurable set, Cantor set is a measurable set, and therefore we use a result that if E is measurable set, then this means that the function chi E is also a measurable function. So this result is conversely also true. So K is measurable set, so this means that the function chi K is also a measurable function. So because of this theorem, this means that chi K is a measurable function and therefore f is also a measurable function. So with this, my first two options have now become correct. Now let us try to see what about the third and the fourth option. Now if you carefully see at the graph of the function, this function is this is a rough graph, this is not a perfect graph. So this function is 0 almost everywhere, but it is discontinuous at the points on the Cantor set. It is a bounded function. It is a bounded function because it lies between 0 and 1. So it's a bounded function. And what are the discontinuities of this function? And we see that the discontinuities, so I'm writing it as df. So discontinuities of the function is nothing but the function is discontinuous at all points which are in Cantor set. So df is actually k. And what is the measure of this discontinuities of this function? The measure of discontinuities of this function is nothing but measure of the Cantor set, and that is equal to how much? 0. So by criteria of Riemann integrability, if a function has discontinuities of measure 0, then this means that the function certainly becomes what? Certainly becomes Riemann integrable. Okay. Now, since the function is Riemann integrable, and we know that if a function is Riemann integrable, it obviously becomes what? It obviously becomes a Lebesgue integrable function. So the function is also Lebesgue integrable, and therefore, when I calculate the Lebesgue integrable, when I calculate the Lebesgue integral of this function on the closed interval 0, 1, I know this closed interval 0, 1 can be written as disjoint union of k and k complement of the function. Since the sets are disjoint, I can separate this as integral of f over k plus integral of f over k complement. What is the value of the function on k? The value of the function on k was 1. What is the value of the function on k complement? The value of the function on k complement was 0. This is k complement. So this component actually goes away because it is integration of 0. So I'm only left with integral of 1 over k, and this we know is a result saying that this is always equal to the measure of k. What result am I using here? That integral of 1 over e is nothing but measure of e. So this result I have used here. And what is measure of k? Measure of k is 0. So we have proved that the Lebesgue integral of the function on the closed interval 0, 1 is how much? 0. And therefore the Riemann integral of the function also has to be equal to 0, because if the function is Riemann integrable, then the Lebesgue integral is the same as the Riemann integral, correct? So therefore the Riemann integral also becomes 0. So this means that our third and fourth option are also correct. So now this finishes this problem.